In this project, we are going to simulate an underfloor heating system with a spiral pipe. The present problem simulates the process of heat transfer through the underfloor heating system by a spiral pipe using ANSYS Fluent software. In this project, a room is designed in cold winter condition and a floor heating system is installed to heat the air inside the room. The underfloor heating system is in the form of a spiral tube that carries the flow of hot water. The hot water pipe is placed inside a layer of concrete and transfers its heat to the concrete layer of the floor. Then, heat transfer inside the concrete layers occurs in conduction, and finally, heat transfer or convection from the ground floor leads to heating of the air inside the room. Air is defined as the ideal gas for the occurrence of free convection heat transfer inside the room's interior. Hot water flows with a flow rate of 0.5 kg per second and a temperature of 303.15 Kelvin enters the pipe to perform the heating process. The present model is designed in 3 dimensions using Design-Modeler software. The calculation area of the present model is related to a room with a length of 3.6 meters, with a width of 2.6 meters, and a height of 2.6 meters, and a layer of concrete with a thickness of 0.12 meter is designed as a solid area in the lower part of this room. Inside this concrete layer, a 0.04 meter diameter spiral pipe is designed to be inserted circumferentially, and after a spiral path across the floor of the room is led out of the room. The meshing of the present project was carried out using ANSYS meshing software. The mesh type is unstructured and the element number is equal to 2,936,179. Now the first step for you to start the simulation is to click on a fluid flow block and then drag it over a blank space in ANSYS Workbench software. Next, right-click on Mesh and then go over Import Mesh File. Then click on Browse and then select the mesh file that is sent to you with the rest of the files. Just like any other type of project, there are several assumptions made in this project as well. For example, the type of our solver is set to be pressure-based since we are dealing with incompressible flows. Second, we have selected absolute format for velocity formulation. And third, we have selected a steady time study since we didn't want our results to be a function of time. Also, you can see here that we have enabled the gravity and its value is equal to minus 9.81 in y direction to calculate the effect of natural convection inside our domain. The next step, expand the model section and then double click on the energy button. Now in the appeared box, you can see that we have enabled the energy equation since we have heat transfer inside our model. Now next, if you double click on the viscous button in the appeared window, you can see we have selected our NGK epsilon model to solve for our turbulent fluid equation, since this model is more accurate than the standard form. Also under the near wall treatment, you can see we have selected the standard wall functions, which are auxiliary functions that help us capture the boundary layer and flow patterns near the wall.
You can buy this learning product to obtain a geometry file, mesh file, and a comprehensive training video on how to set up, meaning the pre-processing, solution, processing, and extracting results, which is the post-processing and analysis.
In this slide, you can easily see the changes of velocity over the plane which you've created in the previous slides. Now in this slide, you can easily see the changes of temperature and how the spiral tubes have heated the interior of the room. And now in this slide, you can easily see the flow patterns over the middle plane which you've created in the previous slide, showing how the natural convection has occurred inside the interior of the room.
To benefit from Mr. CFD services, including simulation, consultation, and training, contact our experts via info@mrcfd.com.